a strike for Black lives in academia and STEM. The purpose of the movement is to hit a pause, to give Black academics a break, and to give others an opportunity to reflect on their own complicity in anti-Black racism in academia and their local and global community. Unfortunately, we, the organizers of the BRAG, learned about this movement at the last minute and did not have time to discuss it thoroughly among ourselves and the many people involved in this memorial session. Speakers, former students, and collaborators who agreed to give their testimonials today. We therefore decided to maintain the memorial session. But, however, we would like to express that we acknowledge that Black people live the injustices of systemic racism, particularly so in Brazil. In life and in academia, people often perpetuate bias and systemic racism, both consciously and unconsciously. This needs to be discussed within our community, and we can no longer be silent. So, with this in mind, we returned to the memorial session in honor of Fernando Torres, our colleague who died last May 28th from complications in his own health. And the first part of the program involves a testimonial from Arnaldo Garcia, his supervisor. So I'm going to put here an audio in Portuguese where he speaks a few words about Fernando Torres' mathematical contributions.
Boa tarde. Estamos aqui para celebrar a vida de Fernando Torres e as suas contribuições na matemática. Fernando sempre foi um grande admirador da matemática, um apaixonado, um trabalhador incansável. Me lembro que, durante a sua tese de doutorado, ele vinha seguidamente ao meu escritório, trazendo sempre ideias novas e outras direções para o seu trabalho de tese. Eu diria que uma posição central do seu pensamento, como matemático, Fernando tinha a teoria dos pontos de Weierstrass e dos seus semigrupos numéricos associados. Sua tese de doutorado trata da natureza desses semigrupos de Weierstrass em recobrimentos duplos de curvas algébricas. Depois do advento do trabalho fundamental de Stöhr-Voloch, que prova a hipótese de Riemann, ou seja, o famoso teorema de Herivelto, introduzindo uma teoria similar à teoria dos pontos de Weierstrass, Fernando muda de direção e passa a se interessar profundamente pela teoria de curvas sobre corpos finitos. Ele se torna um profundo especialista nessa teoria de Stöhr-Voloch, um grande difusor e propagandista dessa teoria. Fernando a utiliza em pesquisas em temas variados, tais como curvas maximais, grupos de automorfismo de curvas, códigos de grupo, arcos planos, etc. Três curvas essenciais sobre corpos finitos aparecem em vários de seus trabalhos. A curva hermitiana, a curva de Suzuki e a curva de Rie. Seus grupos e subgrupos de automorfismo e suas curvas conscientes pela ação destes subgrupos. Eu sempre vou me lembrar de Fernando como uma pessoa doce, tímida e com um grande sorriso contagiante, sempre presente na sua face. grande amigo.
So that was Arnaldo's testimonial. We thank him very much for his words, and we'd like to continue our session with the first presentation of the day by Herivelto Borges, who's talking about the Stöhr-Voloch theory through Fernando Torres' lens. Herivelto, please.
Sorry, can you all hear me?
Yes.
Give me 1 second. I need to share my slides first. 1 second. There you go. Can you all see the slides? My presentation? Yeah?
Yeah, it's okay.
All right, so 1 second, please. Almost there. Okay, so let me get started. First of all, I want to thank the whole committee for organizing this special session for Fernando. We all know he deserves, of course. And I also want to thank for the invitation and all for our audience for coming. I know, I mean, I can see dozens of familiar names. Good to see you all here. And yeah, let me get started. So as you can see from my title, today I'm going to talk about Stöhr-Voloch theory through Fernando Torres' lens. First, I want to apologize to the specialists who are in the audience, including, of course, Felipe Voloch, as I can see. So I'm going to go only over the very basic things. And the reason why I decided to talk about this, as you could hear from Arnaldo, the Stöhr-Voloch theory was the ground for Fernando's most remarkable results, the way I see. So because of this, I think it's worth sharing a little bit of the flavor of the theory, what it is about, and then we go from there. Okay. All right, so let me get started. So here's a very basic question. Let's say you're given a field of 3 elements, and then you can ask, okay, how many solutions? I mean, how many pairs do we have of solutions for this equation down here? It's a very very silly problem and easy to solve. Of course, you can just list all 9 pairs and check them all, and you can easily find that okay, you only have 4 solutions here. Here they are. So it's a very basic question, but as soon as you go a little bit, more to the general case, what if you're given just, a general polynomial over finite field and ask, for the number of solutions to that polynomial equation or the number of, points on the affine curve, things can be, quite challenging, at least in the general scenario. And just to give you an idea, there is this very, famous and celebrated, result by, Haas and Weil, which is known as the Riemann hypothesis for curves over finite fields, that tells you that if you have a curve, let's say X of genus G defined over FQ, well, for the whole talk, by a curve, I'll always mean a projective, non-singular, irreducible curve defined over the finite field FQ. So if you have such a curve, so the Haas-Weil bound tells you that you have at most this number of rational points. So this is a very well-known result and celebrated, and that bound is also sharp, as we all know. There is a very famous curve called the Hermitian curve, which is, I think, of course, it was Fernando's favorite curve, I think. And that curve gives you an example of curve attaining the upper bound given by Haas-Weil. You can easily check the curve has this genus, and with a little bit of computation, you can actually find, count the number of rational points for these curves, and it turns out to be exactly, the upper bound given here. So for such curves attaining the upper bound, they are all called maximal curves. There's sometimes FQ squared maximal, since it all makes sense, and this guy is square. So that gives you a nice bound. I mean, a nice way of addressing my basic original question. But this can be, I mean, we can go further and ask, okay, how is it possible to improve that bound? I mean, how far can we go if you keep working on it? And the reason, and the answer is yes, there are other bounds. There are a few other bounds, but today I'll be looking at this bound called this so-called Stöhr-Voloch bound. And this one is, I mean, something that I usually call baby Stöhr-Voloch, that tells you, hey, if you have a curve of degree d defined over FQ, the number of FQ rational points is upper bounded by this guy here, as long as you have a finite number of inflection points. Let's see how good or bad that bound can be. Just bring a very simple example. Let's say you have a curve of degree 6 over f7, and with this data here, if you go back to Hasse value bound, you compute the bound will be 60, which is pretty bad. But if you apply the Stöhr-Voloch bound, this baby bound, well, considering that you only have finite number of inflection points, which is the case, the bound gives you 36. Of course, it's much better, and more than this, that bound is actually sharp. I mean, 36 is the actual number of rational points for this curve. So the thing is, yes, you can, at least under some circumstances, you can do better than Hasse value bound. But that comes with a price. You see, in this case, I'm already considering a plane curve, some degree d, and imposing the condition that you only have a finite number of inflection points. And this is the general setting for this type of improvement. What you have here, you have your curve, and you have an embedding of your curve, and you have to take into account some data from that embedding. In this case, for instance, I'm requiring the number of inflection points to be finite. So that's the price you pay, but it's worth trying. But as I'm telling you here, this is just what I call a baby version, and that notion or the condition that you see here, the number of inflection points to be finite, can actually be replaced by something more appropriate in the Stöhr-Voloch theory, which is called the Frobenius non-classicality property. Let me just briefly tell you what that is. So suppose you have a reducible curve defined over FQ. The curve is called Frobenius non-classical, with for each simple point on your curve, the Frobenius map takes that point to the tangent line at that point. So as we all know, a picture is worth 1,000 words. I'll just tell you an example. Okay, here is the scenario. You have a point, you have its Frobenius, so here's the tangent line connecting the two. And as long as if your curve satisfies that properties for all the points, which, as you can see here, suppose all the simple points are in this scenario, so you have what is called Frobenius non-classical curve. So it turns out that this type of curve, of course, it's a very pathological behavior, and you may think, okay, this is very rare to occur. It's something specific to positive characteristics, of course. But it turns out that a curve with this property has an infinite number of inflection points in general, if characteristic is not true. So that condition that I was telling you in the previous slide can actually be replaced by this Frobenius non-classical condition, the Stöhr-Voloch theorem. And so here I have another version, which I call now Stöhr-Voloch theorem, which tells you, okay, again, you have a plane curve now of degree d, let's say genus G. So the bound now will be given in this way. So the number of rational points is upper bounded by this number. If the curve doesn't have that strange property, if it's not Frobenius non-classical, so if you play a little bit, okay, just remember GENUS can be upper bounded by this. So if you plug that in, you recover the previous bound that I just showed you in the previous slide. What if you have an infinite number of inflection, or what if you have, or what if your curve is Frobenius non-classical, so the bound is given by this number, so the only difference is pretty much this power of P here. P is just the characteristic of your field. So as you can see already, comparing the two bounds, if your curve is Frobenius non-classical, I mean, chances are your curve will have many rational points. I mean, it's clear that this number, of course, is bigger than this. And just, to mention, one way of, seeing Frobenius non-classical curves, it can be seen as an abstraction to use the nice upper bound, which is the second one, just the smaller one, and which turns out to be the one that I showed you before. And on the other hand, it can also be seen, if you have Frobenius non-classical curves, they can also be seen as a source of curves with many points. And this is something of interest in general. So this is the scenario. I mean, the Stöhr-Voloch, very basic case, but the general result is somewhat more complicated. So I only mention a few things on the setup of that theorem, of the general theorem. So let's suppose you have a curve of genus G, equipped with some base 0.3 linear series, degree G in dimension R. So with that condition, let's suppose you, for each point of your curve, there is this sequence of R+1 non-negative integers here called the dp orders. I won't say much about this. I mean, if you want to think geometrically, just think of your curve, embedding in some Pn, and look at all the intersection multiplicity of hyperplanes with your curve at that point, and you take them all, and that gives you the list of the dp orders. You can think of them in that way. So we have this list of numbers here, and as you might expect, that list of numbers, or that sequence of numbers, is always the same apart from a finite number of points. So always the same means you have this sequence here attached to your curve, which works for pretty much all the points. So given that we have that sequence related to your linear series, now we talk about another sequence. There's another one which is given by those new guys here. Now we have R non-negative integers, and again, I won't tell you where they come from. I'll just tell you, okay, the one fact about those numbers is that you just look at the previous epsilons you had before, and this new sequence will be just a subsequence of these guys. You remove, there will be one guy here with suitable, there will be a suitable index for which you remove one of these guys, then you get what is called the Frobenius sequence. So my point is, when you have this linear system, this linear series, it always comes, equipped with this order sequence, your sequence of epsilons, and also your sequence of the so-called Frobenius sequence. So once you have the two things, now you can easily, tell the general, Stöhr-Voloch theorem, which tells you, okay, under the same, usual hypothesis, let's say we have this linear series of degree D, dimension R, and again, consider the order sequence, the epsilons I just, mentioned, and the Frobenius sequence. When you have the two, so what the theorem tells you is that the number of rational points is upper bounded by this guy here. That's I would say the main theorem, and of course, as you may expect, you can things can, this can be very, very powerful. Let's say you want to upper bound. Of course, you want to make this number small. So the first thing you want to do, okay, let's pick a suitable linear series of some degree D, some dimension R, and of course you have some constraints here. They may not exist depending on the R and D you want. So that is already one challenging part to apply this. The other thing is you want that to be defined over FQ, which is another very suitable condition. And the other thing is, once you have that linear series, let's say you know the dimension degree, you also have to have control of this sequence here. If you know what those sequences are, okay, then you have you have the upper bound here, or you can. The idea is to make this number as small, somewhat small. And what I should mention here, actually, talking about Frobenius non-classicality, you see the Frobenius sequence here. You have the sum of the guys up here. If you bring to this general context, Frobenius non-classical means that this sequence is not the sequence from 1 to r minus 1. So, in other words, if your curve is Frobenius non-classical, that means this sum here will be, bigger than this sum. So the best case scenario for this guy to be small or somewhat small is when your curve is Frobenius classical with respect to this linear series. So, and the idea is, okay, if you want to apply Stöhr-Voloch, so you have a curve, you have to come up with this linear series, an appropriate linear series. You have to have control of all those constants there, and this is a very challenging thing. It's even, if you consider the most basic, let's say a Fermat curve of degree d, and consider, Veronese embedding in general, we don't know those numbers for all the cases. So as soon as you have all this data you want, and they fit nicely here, so you are in heaven. That's the idea. And that was pretty much what Fernando, tried to do for many years. He brought, the Stöhr-Voloch theory to the set of maximal curves. And in that setting, there is a very, special, very, interesting linear series in this, let's say, in this setting of maximal curves, for which, we can, investigate all this data here. And of course, there is still a lot to discover there. But Fernando made a lot of progress, in that setting. And there was, I'm sorry, I have a final slide here mentioning, exactly this work. So because, as I told you, the Stöhr-Voloch theory was the ground for, many of Fernando's remarkable work, like remarkable results. And the idea was, he had like a very deep understanding of the theory, and he was able to bring those two things together, like Stöhr-Voloch theory and this setting of maximal curves. And in there, using this so-called Frobenius linear series, I won't say much about this because I know Saeed will come after me and say about and discuss a little bit about this, I think. But the idea was he will bring all that theory to this setting, and he was very successful in making progress and proving lots of nice results about maximal curves. It was really a huge legacy from Fernando in that sense. So, and just to finish this, I would like to mention, within this setting, my favorite result by Fernando, which is actually by Fernando and Professor Gabo Koshimaros, is what is called the natural embedding theorem, that tells you pretty much that any maximal curve is actually embedding in a Hermitian variety in some projective space. And this is, it's not only beautiful but very useful and nice result. That's the one I choose for today. And just to finish, I really want to say, Fernando, that we all appreciate all the time, that we worked together, that we lived together, that while he was here, he was really valuable for all of us. So Fernando, rest in peace. That's it.
Thank you, Herivelto. So now please, we go to Saeed's presentation. So Saeed, please.
Good afternoon, everyone. Please let me share my presentation. Okay. Okay. You can see the slide.
Yes, we can. Thank you. So now
Okay.
I'm asked to present Saeed Tafazolian from the IMEC, who will talk about maximal curves over finite fields. Saeed, please go ahead.
Thank you, Jahvin. First of all, I want thank you, thanks organizer for giving this opportunity. Clearly, it is a pleasure for me to talk about Fernando and also for his research work. Today, I want to present some results of him about maximal curves. First, I fixed some notation. By curve, I mean a projective non-singular algebraic curve. By FL, I mean a finite field with L elements, and the CFL is the set of rational points of the curve with other FL. Okay, as in the presentation of Herivelto, we have seen there is a Hasselblad bound for the number of rational points of a curve of a finite field, and when the number of elements of finite field is squared, a curve C is called maximal over Q squared if the number of rational points of C attain the upper bound. Maximal curves have several interesting applications in mathematics, in particular in coding theory, cryptography, and others, and also in geometry. Is well known as a supersingular curve. Here, first, I want to review some property of maximal curve. First, we know if a curve X is maximal over K, then the L polynomial of the curve is the power of a linear polynomial. Using this and using some arithmetical and geometrical properties of curve, we can find some geometric information about the Jacobian, acting of Frobenius and Jacobian of the maximal curve. We can use these nice property of a characteristic polynomial of the Frobenius, and as we don't have enough time, I explain this property only for maximal curves. In the case of maximal curves, we can show the characteristic polynomial of the Frobenius acting of a Tate module of a Jacobian of a maximal curve is given by a power of this linear polynomial, and this says that the Frobenius map of a Jacobian of a maximal curve acts as a multiplication by minus k of a Jacobian, and this implies that if we have a maximal curve C and given two rational point P0 and P1, we have a linear equivalency between these divisors. It does mean we can consider this, or we can define this linear system, and by this result we can see this linear system is a FQ squared invariant of the curve. In particular, its dimension is independent of the choice of the P0, and also one can show that this linear system is simple and is base point free. So we can apply Stöhr-Voloch theory for this linear system. Okay, I say, I want to explain. I want to present some results of Fernando Torres about the maximal curves. But in maximal curve, there are three important problems on maximal curves. First, determination of the possible general maximal curves. Second, determination of explicit equations for maximal curves, and also classification of
your presentation.
Yeah.
Your presentation has stopped.
Excuse me. Okay, I try to share again. No, it's okay?
Yeah, now it's okay. Thank you.
Oh, thank you. Excuse me. Okay, as I said, there are three important problems on maximal curves. The determination of the possible general maximal curve, determination of explicit equations for maximal curves, and also classification of maximal curves of a given genus. Fernando has several interesting results for each of these problems that I want to present some of them here. There is a main problem about the general of a maximal curve. There is a problem suggested by Jean-Pierre Serre that describe the following set. When we fix a finite field, we describe all integers such that there exists a maximal curve of genus N. There are only finite many possibilities for the genus G of the maximal curves, since Ihara has shown the following result. Ihara has shown if the curve C is maximal of F2 square, then the genus of the curve C is bounded by this number. And clearly, there is an example for the upper bound, this upper bound, and also the rational curve is also a maximal curve. So we can see that this set that we can call a spectrum. This spectrum is a subset of this interval. Now we can ask about the classification of a maximal curves of a given genus. There is a result by Rook and Sistenus that there has shown there is a unique maximal curve which attains the above genus bound, and it can be given by the affine equation. This is the so-called Hermitian curve. Okay. After this result, Sistenus and other people tried to find more information about this set, and they gave this conjecture. They guess there is a gap in this interval for the genus of maximal curves, and they gave this conjecture in this paper. If the curve C is maximal of genus G, then or the genus is the upper bound, or the genus is not bigger of this number. This is the point that Fernando has done the first his work on maximal curves. Fernando has considered this linear system for maximal curves, and by applying Castelnuovo genus bound with Reiner-Fuhrmann, they have shown the following result. They have shown if there is a maximal curve of F2 square of genus G, the following statements are equivalent. they studied the dimension of this linear system, and by study the Frobenius order and sequence of order, such sequence order that you have seen in the presentation of Herivelto, they have found this nice result that if they have shown if the dimension of this linear system is 2, and there is a unique maximal curve, and this maximal curve is of to a Hermitian curve, and here he has the genus bigger of this number. The result is published in Manuscript Math. And after this, I mean, by using this result, we have proved the conjecture supposed by Shins and Stöhr-Voloch. I mean, this is first result of Fernando about the maximal curve, and is very interesting result. So we can see up to here the spectrum of a general maximal curve is a subset of this interval union this number. And for this number, we have seen there is a unique maximal curve have shown by Stöhr-Voloch and Rook. And what about this number? For this number, there is some result due to Fernando and others. First, in art characteristic, Fernando with Rainer Fuhrmann and Arnaldo Garcia, using again the study the sequence of order sequence and the Frobenius order sequence attached to the that linear system. Among other things, they have proved the this result. I mean, they have proved there is a unique maximal curve of given this genus that given by this equation. The result has published in Journal of Number Theory. And in characteristic 2, Fernando with medium atom with extra condition have found some characterization for a maximal curve of the above this genus. I mean, they have proved if there is a maximal, if C a maximal curve of this genus, then the curve C is F2 squared isomorphic to the one given by this equation. And the result published in Manuscript Math in 1998. And again, clearly, Fernando has done several results with several people, but in this direction, Fernando has done a work with Professor Gabor Korczmarus and improved his results. I mean, there has shown, let's see, be a maximal curve over the G, then we can find another gap in the interval of a spectrum of a genus of maximal curves. I mean, they have found this nice result, that their result published in this paper. Okay, clearly Fernando had several results about the maximal curve, about the classification of maximal curves, and here I want to rapidly present some work that I have done with Fernando. We have the first paper work about classification of Fermat type curve. After we try to classify some maximal curves given by this equation. After we try to find some explicit maximal curves which cannot be covered by the Hermitian curve. We have some classification on certain maximal curves, and recently we have find some new equation for maximal curves using Chebyshev polynomial, and with Nazar we have find some information about spectrum of the genera of maximal curves of an SMR fields, and again using the Stöhr-Voloch theory we can find some classification for the recurve, and also another classification for some explicit maximal curves. Thank you.
Thank you, Saeed. Thank you very much, Saeed.
Welcome. Yeah.
Very nice. So let's move to our third speaker, Luciane Quoos. Luciane, you have the screen and the microphone.
Okay, thank you very much. I'll try to put my slides on. So that's from here. I think Saeed is still presenting. Should he stop or?
You can present on top.
I have stop.
Okay. So I can go here. Okay, let's see. So can you see?
Yes. So I'm glad to introduce Luciane Quoos, who make a tribute to Fernando Torres.
So, dear colleagues, I'm glad to share with you some aspects of the research of Fernando Torres. And I'd like to start saying that besides being an excellent mathematician, Fernando Torres was also known for being very kind and simple and a humble person. Fernando Torres would discuss mathematics with anyone wanted to discuss some subject. He was really like an open mind to discuss math with everyone. And also to me, the relation of Fernando Torres with his students was very important. The students for him was like a family. We can say that actually it was quite usual that the students would go at his place to study or stay at his home during scientific visits. This is how Fernando was. And so this is a photo from 2011 when the Beatriz Casulari, she's here, PhD thesis defense. So you can see here is Cícero, Gilvan, Herivelto, Fernando, Beatriz, myself, and Brumati. Okay. And well, since the students were so important to him, I think it was important to show their names here. And to show Fernando contributed to the new generations of mathematicians in supervising 11 PhD students during 14 years of his career as a mathematician. So these students, they all have got positions as positions in Brazilian universities. You can see Mateus is working at Brasilia now. Wanderson has a position in Goiás. Steven and Paulo César in Pernambuco. Well, Arnaldo actually has a position in Colombia, is the only one that came back. Beatriz has a position in Minas Gerais. Actually, Beatriz, Rafael, Alonso, and Guilherme, they 4 have positions in Minas Gerais. Juan has a position in Mato Grosso, and Ercílio is in São Paulo. So we can say that we have a little of Fernando's memory in all these states in Brazil. Well, I'm talking about Fernando research on coding theory. I'm going to avoid the part on Weierstrass semigroup since Cícero, that is the next one to talk. Probably we'll talk about that. Okay, coding theory and the Weierstrass semigroups that has a lot of connection. So these are some of the collaborators of Fernando's coding theory, and I'm talking about this work with these persons. So I start like, well, say what is an algebraic geometric code. So we start with an algebraic curve X over FQ of genus G. Then you fix 2 divisors, D, that is the sum of n rational points on your curve, X, and G can be any divisor such that these points P1 to Pn are not in the support of G. So using this, the curve and these 2 divisors, you can define 2 different types of codes. Okay. So you have the linear code that are associated to the Riemann-Roch space defined by G. So we evaluate functions in LG, the functions on P1 to Pn. And there is also a second way to define algebraic geometry codes using the space of differentials. So you compute the residual of the differentials on these points, P1 to Pn. So these both codes are actually subvector spaces of FQ to the n. And we say that they have dimension k. And also the minimum distance d. Okay, so when I give you a code like this, or the linear or differential code, we say that it has length n, dimension k, that is the dimension as a vector subspace, and the minimum distance d. So what is the minimum distance of a code? The minimum distance of a code can be seen as the number of non-zero coordinates of a code word in your code. Okay, so you take all your code words that are non-zero and you compute and you see how many entrances are non-zero. So the minimum of this value is the minimum distance d. Okay. And there are 2 classical bounds for the minimum distance of these codes. So the linear code, the classical bound is n minus the degree of g. And for differential code, the classical bound or the GOPA bound is degree of g minus 2g minus 2, where g is the genus of your curve, underlying curve. So you can see, for example, that if you want a code, error correcting code, that's a code that can correct many errors. You want a large minimum distance, so you want n to be large. So you want a curve with many rational points. And so many constructions of explicit algebraic geometry codes over curves are over curves that are maximal curves, the curves that Herivelto and Saeed has just talked about. Also, these codes, the linear and the differential one, they are dual codes, dual in the sense of the standard inner product over FQ. And C omega can also be seen as isomorphic to another actually linear code. So you can also see the C omega as a linear code for another divisor G, depending on a certain divisor, on another divisor. Okay, so when you have, when the divisor G is of this type, A1, Q1 plus AM, Q to the S, QS, where A1, AM are just natural numbers, we say that this code is an n-point code. Okay? And people have studied a lot like codes in many points. So the code, linear code, and also its dual. Okay, so what kind of things people are interested in the research, like in the computations of the parameters of the codes, N, K, and D, like improvement of the parameters, I mean the improvement of the minimum distance of the codes, and also special properties. What are special properties? You want to study like self-dual codes, or also you can study like locally recoverable codes, quantum codes, so you have a special kind of codes. Okay? And now we'll start showing something like well, related to the work of Fernando. So for example, if you fix Q, a rational point on your curve, and you look to you make G equal to, well, Q a rational weight on X, and you consider the Weierstrass semigroup at Q. So it is ρ1, ρ2, etc. And let C be the conductor of the semigroup. So what's the conductor? It means that from C, everyone is in the semigroup. Okay? And now you consider the code C, that is just the dual of the linear code defined by D, and your divisor G is ρ index M times Q. So ρm is any guy in the semigroup at the point Q. So if you do this, now you can define these like a priori sets that are called, you look to fix L, or L is actually larger or equal than 1, and you look to the all pairs, S and T, such that when you add two guys in the semigroup, you have this whole L. Okay? You have the fixed non-gap. So, and now you say that L, like for example, is the number of the guys in this set, A, L plus 1. So there is a order bound. This is a result from Frank-Rao, that if you define the order of this code, C, the code should be C just as the minimum of this value, then you have that this bound is always larger than the classical GOPA bound, okay? And the distance, the minimum distance of your code is always larger than this one. So this improves the classical GOPA bound. And of course, since you want the minimum of this sequence for L larger than M, if this sequence is an increasing sequence, it's easy to compute this value. So for example, you have a result from Munera and Torres, where they showed that the minimum integer R such that the sequence is strictly increasing is R is equal to 2 times the conductor minus G minus 1. In this work, they also worked out the sequence over certain special semigroups. Okay, there was like accurate semigroups. They were continuing a work from Maria Braz Amoroso on semigroups. And this bound here is like when you have the Weierstrass semigroup in one point, this bound was generalized for more points from by Dursma, Kirov, and Park. There is also another bound related with a work of Fernando, that is a work that joined with Gayo, Munera, and Ruano, that now you fix your divisor D like this again. And now instead of looking at the semigroup at the point Q, what do? You look at all the natural numbers M such that you have a jump on the codes, we can say. You have different codes from me minus 1 times Q, and the code defined by MQ. So, of course, since your codes are always inside of FQ to the n, so you have exactly n of these values. And this is always contained in the semigroup, these values. Okay. So now if you fix an element in capital H star, and in a similar way, you consider these sets, gamma I, now you want that m minus fixed mi, you want all the guys m such that m minus mi is in H star. Then they proved that the weight of C is always larger than the cardinality of the set for all the words that are in this code and are not in this code. So in particular, if you take the minimum of the cardinality of these sets for all r smaller than I, you have this theorem from Gale, Munera, Ruano, and Torres, that for a non-negative integer m, we always have that the minimum distance of the code is larger or equal than d star in the dimension of this called CL, D, and Q. Okay, so they also tried to relate this bound with the bound we had before. And actually, they have shown that for the case of okay, just a minute. For the case of okay, yeah. For the case of isometry dual codes, you have that actually this both this bound on the minimal distance of codes and the bound in the last slide, they are exactly the same. So here are like the papers. This is one from the Munera and Torres, the first one from 2008. And this is the second one from 2000, this one from 2011 on the other bounds for 1.8G codes. Okay, they also, yeah, this is one theorem in the paper, but they also constructed many codes over some families, and they tried to compute this kind of bounds. This is usually a really difficult task to do. Okay, so one more thing is that when we study the dual of one point code, so we have a code just in the point Q, it's not always the case that the dual is a one point code. So for example, it will never be self-dual code. So that was a question like, do you have algebraic curves such that the dual of a linear code is the dual of a one-point linear code is again a one-point linear code? So Fernando has also worked in this subject. And let me talk a little bit about that. So I start from, there is a result from Liuvitz from 1990 that says that if you take any rational point on your curve X, then the number of rational points on your curve is bounded by Q. So you are looking to points over FQ is bounded by Q times. This is the second known gap at Q plus 1. Okay. And so Fernando, they worked with the so-called Castle curve. And this is funny because the name of the curve is being Castle. It's just because they had the idea of this kind of curves in a conference. And this conference was in a castle in Europe. So this is the name Castle curve. So they define the Castle curve as a curve such that you have an equality in this bound. And also the semigroup on Q is symmetrical. Okay, so do we know some Castle curve? Yeah, we have some well-known curves that are Castle curves, like the Hermitian curve over FQ squared. So the Hermitian curve has just one point at the infinite, and the semigroup is generated by Q and Q plus 1. And the number of rational points is just q to the cube plus 1. And so this is q squared times q plus 1. Remember that the first element, the semigroup, is always 0. So whole true actually is always the first non-zero element. We also have the norm trace curve over fq to the r. And well, this curve is just, you look to the norm from fq to the r to fq, and you look to the trace from fq to the r to fq. So you compute norm in y, and you compute like a trace in x, and you put it equal, and then you get the equation of your curve. So this is generalization of the Hermitian curve. And well, the Weierstrass semigroup at the infinity has just one point at the infinity, generated by this guy and this guy. And then again, the number of rational points is just q to the r times this is whole 2 plus 1. So for example, these are Castle curves. So in his work, they have, well, showed many examples of Castle curves. They even investigated like non-Frobenius classical curves that were Castle curves. So for example, they have proved that the line Ludwig curves like Hermitian, Rhea, and Suzuki, they are all Castle. And they also gave like many conditions to a curve to be Castle curves. And they worked the codes on these Castle curves. Okay, so this is a work from 2009 by Monheira, Sepúlveda, and Torres in Advances of Mathematical Communications. And Fernando has also other works concern algebraic codes. So this is about like quantum error correcting codes. So here we have just the definition: a K-ary quantum error correcting code of length n and dimension k is actually a k-dimensional linear subspace of c to the q to the n, where c is the field of complex number. And well, King and Matthews in 2008, they found a way to obtain quantum codes from linear codes over FQ. Okay, and for this construction done by them, the knowledge of the code and the dual of the code is important to get the quantum codes. So, like in 2016, Monheira, Tenorio, and Torres have worked on the constructions of quantum error correcting codes over Castle curves. Since Castle curves is really the right way to work with dual codes in one point. Okay. And even more recently, like now in 2020, Fernando and Tenorio and Carlos Monheira, they have worked on locally recoverable codes. So what is this? So a locally recoverable code is a code that if I give you a code word and it's missing one coordinate, then you can recover that coordinate for a small subset of other coordinates. And the people has been working a lot with this kind of codes. Now we have like even locally recoverable codes with more than one recoverability at this point. And they work with this kind of codes from curves with separated variables. And well, they gave a way to construct the locally recoverable codes from this type of curves. And they also provide many examples of codes of this type over some well-known curves, like the Hermitian and norm trace and this kind of curves, maximal curves. And there is also other contributions on the theory of algebraic geometry codes, like Fernando has also worked on computing like Grabiner bases for norm trace curves, norm trace codes, and also like he worked on codes over generalized Hermitian codes. These are codes over a certain generalized curve that generalizes the Hermitian curve. Okay, this is a work from 2013, and I'd like to finish on showing like this is a draw done by undergraduation Fernando's student. I don't know the name of the student, but this is on his page also at UNICAMP. And I think it's very nice one. And I'm just here to support what Marcio, what people in the beginning of the conference, people talked about. We should care more about Black people in academy and the issues and the issues related to them. Okay, we should be more supportive. That's it.
Thank you very much. It's your turn. Cícero, where are you? Luciane, you may want to stop sharing your screen.
Okay. Yeah, I can do that, but.
Go to these little three dots.
But if you just put your over, it goes over. So.
No, yes, it does, but Cícero is taking a while.
Okay. So let me just see.
Liga o microfone, Cícero. Você está sem microfone.
Well, I don't know how to. Okay, let me see here. Huh? Okay.
Yes, very good.
Okay.
Tenta ligar o microfone do Cícero. Eu acho que por alguma razão ele não está conseguindo ligar.
Ele está sem microfone e está sem vídeo também, né?
Não, o vídeo está aparecendo.
Ah, é? Para mim não está aparecendo o vídeo dele.
Talvez o Cícero tenha que sair e entrar de novo, porque quando você entra no Google Meet, só aparece uma janelinha dizendo permitir usar o microfone, permitir usar a câmera.
Não, mas ele estava falando mais cedo, estava usando mais cedo, eu acho. Você consegue? Ah, ele saiu.
Ele saiu, ele deve estar com problema para
ele ouviu a Luciane e concordou visualmente. Está no processo de sair e voltar.
Ele fez leitura labial.
Não, ele ouvia a gente.
I was hearing you. I was having some problem with the sound.
Okay, good.
Now we can hear you.
Yeah.
So let me start. Let me try to share my screen. So can you see my screen now?
Yeah, it's coming up, yes.
Yes.
Okay, thank you.
So I'm very glad to introduce our last speaker of the day, Cícero Carvalho from Uberlândia, to talk about Leicester semigroups. Please, Cícero, go ahead. You have the microphone.
Thank you. Can you hear me?
Loud and clear.
Can you hear me now?
Yes,
Yes.
we can hear you.
Okay, thank you. So I would like to thank the organizers of this seminar for setting up this tribute to Fernando, and also for inviting me as a speaker. So what I would like to do is to make a brief account of Fernando's works dealing with Weierstrass semigroups and related topics. As Arnaldo said, Fernando's work has always been permeated by the concept of Weierstrass semigroups, and also concepts derived from it. His interest in these semigroups started, as also Arnaldo said, with his thesis, which is entitled Weierstrass Points and Double Coverings of Curves of 1993. So in this presentation, a curve will always mean a projective non-singular irreducible algebraic curve. So you take X to be a curve defined over an algebraically closed field of characteristics 0. And you take a gamma to be a non-negative integer. So he calls X a gamma hyperelliptic curve if X is a double covering of a curve of genus gamma. So hyperelliptic curves are an example of a gamma hyperelliptic curve. It's well known that if Y is a curve of genus G greater or equal than 2, then you have the following equivalences. Y is a hyperelliptic curve. There exists a point in Y such that this HP is the Weierstrass semigroup at P. So there exists a point where the Weierstrass semigroup is hyperelliptic, meaning that 2 is an element of the semigroup. And there exists a point in Y such that the weight of P or the weight of the semigroup is G choose 2. The weight of the semigroup is just the first gap minus 1 plus the second gap minus 2 until the last gap minus G. So in his thesis, he generalized these equivalences to gamma hyperelliptic curves. And for that, he introduced the concept of gamma hyperelliptic semigroups. So he called a numerical semigroup a gamma hyperelliptic semigroup if the first gamma positive integers m1 to m gamma are even, m gamma is 4 times gamma, and 4 times gamma plus 2 is in the semigroup. The main results in his thesis are first this theorem that says the following: take X to be a curve of genus G in gamma non-negative integer, assume that G is greater or equal than 6 gamma plus 4. Then he proved the following equivalences. Gamma is X, the curve is gamma hyperelliptic. There exists a point P in the curve such that the Weierstrass semigroup at P is gamma hyperelliptic. And there exists a complete base point free linear system on X of projective dimension 2 gamma plus 1 and degree 6 gamma plus 2. So in his mind, this was a generalization of this equivalence between 1 and 2 here, okay? As for the equivalence between 1 and 3, he proved this theorem. Let X be a curve of genus G, greater or equal than 30. And let's say if the genus is large enough, then we have the following equivalences. X is gamma hyperelliptic. There exists a point P in X such that the weight of the semigroup is in this range. And later, he would also study these inequalities. I'll talk about this later. And also, there exists a point P such that the weight of P is in this range of numbers. So this would generalize the equivalence between 1 and 3. And using techniques from Fernando's thesis, Stöhr proved the existence for any genus greater than 99 of symmetric gamma hyperelliptic semigroups, which cannot be realized as Weierstrass semigroup. So this was also an important thing. So he presented his thesis in 1993. In 1994, he stayed at IMPA for a period of postdoctoral studies, 1 year. And he started to work on a generalization of the results of his thesis. So for this, he introduced the following concepts. So take again X to be a curve of genus G, now defined over an algebraically closed field of any characteristic. Take n and gamma to be integers, n a positive integer, gamma greater or equal than 0. So he defined a curve X to be of type n gamma if it is an n-sheeted covering of a genus gamma curve with at least one totally ramified point. And he defined the companion concept of numerical semigroup of type n gamma. So numerical semigroup is said to be of type n gamma if the following conditions are satisfied. The semigroup has gamma positive multiples of n in the interval n to gamma n. The gammath element of the semigroup is 2 times n times gamma, and 2 times gamma plus 1 times n is in the semigroup. Of course, when n equals 2, we have the concepts of his thesis, the gamma hyperelliptic curve and the gamma hyperelliptic semigroup. So consider the following statements. X is a curve of type n gamma. There exists a point P in X such that the Weierstrass semigroup is of type n gamma. There exists a point P in the curves and a positive integer A such that the linear series associated with the divisor A times n times P is base point 3 and has dimension A minus gamma. So in a work completed in 1995, and he was at a CTP where he stayed for 2 years, also in a postdoc visit, he presented several conditions that guarantee that some of the items above imply another one, assuming that n is prime. As a corollary of his main results, for example, he proved that if G is large enough, then 1 is equivalent to 2. And he also used the Stöhr method to describe several semigroups, which cannot be realized as Weierstrass semigroups. A part of the paper is devoted to study some properties of numerical semigroups of type n gamma. So there's no geometry here. So a study of numerical semigroups. And he liked that. So he decided to do a further investigation of these properties. And he started with the case where n equals 2. So he started with the case with the semigroups which appeared in his thesis, the gamma hyperelliptic semigroups. So in 1997, he published a paper with results on the gamma hyperelliptic semigroups. In it, he proved that if the genus of the semigroup is large enough, many properties which characterize gamma hyperelliptic Weierstrass semigroups are shared by any gamma hyperelliptic numerical semigroup. And we know from the Stöhr result of his thesis that there are gamma hyperelliptic numerical semigroups which cannot be realized as Weierstrass semigroups. So this was a nice paper. And then in a paper which appeared in 1998 with Rainer Fuhrmann, properties of Weierstrass semigroups were used to characterize the so-called Suzuki curve, using its genus and number of rational points, as Saeed talked about that. In a paper published in 1999, written with Ruud Pelikan, he started to make applications of Weierstrass points to coding theory. So he started by using them to calculate the redundancy of some codes. Redundancy is just the length minus the dimension of the code. The next few years were devoted mainly to the study of maximal curves. He only returned to the study of semigroups in 2002. This doesn't mean that he didn't use, as we saw in Saeed's talk, semigroups, Weierstrass semigroups in the study of maximal curves. But they were, let's say, it was not the main point of the papers. In 2002, he invited me to Campinas for a week. And he gave me several lectures on his recent work on maximal curves and the old works on semigroups. When I visited him, I was really, what can I say? I was shocked by his generosity. He at that time he was living in a small house with just one bedroom, and he insisted that I would sleep in the bedroom while he would sleep in the couch in the living room. There was no way to take this idea out of his mind. And also in the lectures, he gave me so many lectures on maximal curves and semigroups, and he would share everything that he knew about these topics, his ideas, his insights, tricks of the trade, everything. So he was extremely generous to me, not only in that time, ever since I knew him, but at that time especially, it was amazing. So after all those talks, he proposed that we extend to semigroups of type n gamma some results he had obtained back in '97 for gamma hyperelliptic semigroups. And we did a paper which appeared in 2003. And in this paper, we proved, among our other results, the following. You take a numerical semigroup, you take n and gamma integers, n greater than 0, gamma greater than 0, and a prime number. So H is of type n gamma if and only if 2 gamma n is in the semigroup, and the n gamma plus 1 positive element of the semigroup is the number n plus 1 times n times gamma plus n. We found still another characterization for semigroups of type n gamma with n prime in this paper, and we also determined a sharper lower bound for the weight of the semigroup. So of course we wanted to find a range for the weight of the semigroup, but we only succeeded in finding a sharp lower bound. So in 2004, it was my turn to invite him to do a joint paper, now generalizing properties of Weisser semigroups at a pair of points, which have been studied in the past years by Homa and Kim. So let me explain what these semigroups are. You take a curve of genus G, defined over a finite field FQ. You take Q1 to Qm to be rational points of X. So the Weisser semigroup at this ordered set of points is just the set of m tuples with non-negative integers as entries, such that there exists a function in the function field of the curve, such that the pole divisor of the function is of this form, n1 q1 plus O1 plus nm qn. So this is the Weisser semigroup at several points. Now you take n distinct rational points of X, also distinct from the previous Q1 to Qm. Let's Q1 to Cm be non-negative integers. The image of this FQ linear map. So here we have a map from a space of differentials associated to this divisor to FQ to the n, where you take a differential and you associate this n tuple, which are the residues of the differential at P1 to Pn. So you can do this because of the differentials belong at this space associated to this divisor. So this is the image is a type of code. The image of this map is a type of code. It was introduced by Gopa. He proved that this number is a lower bound for the minimum distance of this code. And we proved that if one chooses certain gaps in the Weisser semigroup at these points, say A1 to AM and B1 to BM, these are gaps, meaning that they do not belong to the semigroup. And then we define CI as being AI plus BI minus 1 for all I. Then a lower bound for the minimum distance of the code is the Gopa bound plus M. So we get a better lower bound. And we also determine other conditions for the gaps, which assure that the lower bound is even higher. In the past decade, Fernando supervised 3 PhD theses on semigroups, which resulted in 3 publications with collaborators. So in the thesis of Juan Villanueva, published in 2010, they investigated the true values of the weights of gamma hyperelliptic semigroups. Remember that I told you about the range of the weight, where the weight of the semigroup was. This range. So for some gamma hyperelliptic semigroups, they described the exact values of this weight. And in the thesis of Matheus Bernardini, which appeared in 2017, they studied the number of semigroups having a given genus, and also having, besides having the same genus, the same number of even gaps, with methods which again were motivated by results he had obtained back when he studied gamma hyperelliptic semigroups. In the thesis of Wanderson Tenório, published in 2019, they studied the relation of generalized Weisser semigroups at several points these generalized Weisster semigroups were defined by Félix Delgado, and then also studied by Billy and Tutas. So they studied the relation between this semigroup and Poincaré series associated to it. And they proved that the series completely determines the semigroup. Fernando also worked with generalization of order functions. This is a concept which was introduced by Roholt, Lind, and Perican, and were also related to Weisster semigroups, and they appeared in the thesis of Ercílio Silva and Rafael Peixoto. Well, I don't have time to go into details of these papers. But so this was a very quick survey of Fernando works deal with Weisster semigroups. And so I thank you for coming to the seminar. I also thank Fernando.
Thank you very much. Thank you, Cícero, for sharing these pictures and your friendship with Fernando with us. Now, to complete our seminar, our special session today, we have a video with testimonials from several of his students, previous and current. And I think, Caroline,
I will. Yes, I will. I will share. I will try to show you my camera, or I can actually try to share. Cícero, can you please stop sharing? Somehow I cannot. Okay, now I will try to. Can you see the screen now?
yes, it's coming up. Yes, it shows.
Okay, so I will try to do something here, try to start both computers at the same time, and let's see if that works.
Meu nome é Ercílio. Tive a honra e a grata satisfação de ter sido aluno de doutorado do Fernando. No caso, fui o primeiro, um privilégio enorme. Tivemos também alguns trabalhos em conjunto, mas eu gostaria aqui de falar um pouco sobre a pessoa dele. Extremamente generosa, atenciosa com todos e a qualquer momento sempre solícita às nossas demandas. Levo essa ação como um legado dele, né? Procuro fazer o mesmo, sempre da medida do possível, com os meus alunos. Entendo que dessa forma é uma maneira de levar a vida do Fernando adiante, né? Com muita atenção e dedicação às pessoas que dependem da gente em determinado momento da vida.
Eu sou o Guilherme, fui orientado pelo Fernando entre 2005 e 2008, no doutorado, e além de ex-orientador, o Fernando era um grande amigo. Ele era um cara muito gentil, muito legal, e uma característica muito bacana dele era dar essa abertura para os alunos, para se ter uma amizade com ele. Eu acredito que todos os ex-orientandos dele, uns mais, outros menos, mas tiveram uma relação de amizade com ele. Então isso eu acho que era uma característica muito legal dele. Bom, era um grande matemático, merece todas as homenagens e vai deixar muitas saudades. Um abraço.
Eu sou Alonso, eu fiz mestrado e doutorado junto com o Fernando, tive o privilégio de compartilhar bastante tempo junto dele. Posso destacar, lembrar dele a sua simplicidade, o seu acolhimento para com os alunos, com seus colegas, com seus amigos. O Fernando foi bastante apaixonado pela matemática, um pesquisador de ponta na sua área. Aprendi bastante com ele durante seminários, durante o tempo de trabalho, e destaco as inúmeras experiências que ele compartilhou junto comigo através de tomar o seu famoso suco canônico, suco que ele pedia de laranja, caju e acerola. O Fernando influenciou a minha vida profissional e pessoal. Um abraço.
Olá, eu sou Juan, conterrâneo do Fernando. Fui orientado dele no doutorado. O Fernando foi uma pessoa maravilhosa, um grande amigo e um ótimo orientador. Era muito apaixonado pela matemática e um excelente pesquisador. Além de matemático, era escritor de contos breves, muito legais, que deixará saudades e angústias pelo final deles. Assim como os seus amigos falam sobre o suco canônico, ele tinha um gosto também pelo café expresso, que ele gostava muito. Tive muitas experiências com o Fernando e o privilégio de conversar com ele dias antes da sua partida. Um grande abraço para todos.
Boa tarde, eu sou Beatriz, fui aluna do Fernando de 2007 e 2011. E eu lembro bem, quando eu cheguei lá na Unicamp e fui conversar com ele, falei, eu queria ser sua aluna de doutorado, eu estudei com a Luciane na UFRJ, queria continuar nessa parte de corpos finitos. E ele falou assim, bem, eu vou dar álgebra comutativa, você faz, se você for bem, a gente conversa. Falei, tá bom. Um dia a gente estava saindo da aula e ele falou assim, Beatriz, vai na minha sala mais tarde para a gente ver o que você vai estudar. Eu falei, Fernando, não era para eu esperar? Não, isso era eu querendo parecer durão, mas eu não sou durão. E realmente ele não era durão, ele era uma pessoa muito doce, sempre se preocupou muito com os alunos, sempre queria saber como é que eu estava, como estava a minha universidade, ele sempre procurava. E por isso eu vou sentir muita falta dele, como amigo, como orientador, como matemático, vou sentir muita falta. Vai fazer muita falta para todo mundo.
Olá, meu nome é Paulo César, mas Fernando sempre me chamava de PCzinho, né, fui orientando ele de doutorado, né, de 2000 até 2016, acho que eu fiquei mais tempo com ele, e, portanto, eu tive muita conversa com ele, né, durante esses 20 anos. E falar do Fernando é falar de uma pessoa, de um grande pesquisador, né, uma grande pessoa, né, uma pessoa humilde, mas de grande talento para a matemática, é um grande amigo. Né? Então a gente perde não somente um grande pesquisador, mas também somente um amigo, né? Uma pessoa que você sempre podia contar com ele, que sempre lhe apoiava, né? E vai ficar muita saudade.
Olá, que tal? Bom, Fernando era um grande matemático, acho que não há qualquer dúvida com relação a isso. O cara conseguia ver coisas de uma forma que acho que poucas pessoas conseguiam, saber os caminhos, os encaixes de coisas extremamente surpreendentes. Mas Fernando também era uma pessoa extremamente gentil, uma pessoa acolhedora, uma pessoa protetora, um grande amigo. Para toda a obra. Se você estava triste, você podia conversar com ele. Se estava feliz, você podia conversar com ele. Se estava entediado num domingo, você podia conversar com ele também. Um grande amigo de verdade. E com certeza vai fazer falta para todo mundo, né?
Esse sou eu, ao lado de Fernando Torres. Essa foto representa muito bem nossa amizade. Meu nome é Matheus Bernardini e fui orientando de doutorado do Fernando entre 2014 e 2017. Era muito comum ouvir essa música de fundo ao ir até a sala 205 do IMEC. Ela é, na verdade, a música de início de um podcast que Fernando ouvia com frequência. Que Fernando Torres foi um grande matemático, a comunidade científica e seus trabalhos confirmam sem deixar dúvidas. Fernando foi também um exemplo de pessoa, alegre, bem-humorado, com um coração gigante e muito querido. Era torcedor do Guarani e torcedor fanático do Barcelona. Fernando adorava futebol. A triste notícia de sua partida percorreu o Brasil e o mundo e mobilizou diversos de seus amigos e familiares. Muitas mensagens de solidariedade foram compartilhadas. Ele esteve aqui em Brasília nos últimos 2 verões e seu restaurante favorito foi, sem dúvida alguma, o Mangai. Fernando deixará muita saudade e um legado que estará vivo para sempre.
Falar de Fernando é relativamente fácil. É uma pessoa muito carismática, né? Entusiasmada, né? Com convívio com os colegas da sua volta, fazia com que o convívio com ele fosse muito bom, muito bacana. Sempre cativava todo mundo, mantinha todo mundo motivado. Então, essa é a minha principal lembrança de aluno dele, né? Fora do ambiente acadêmico, eu conhecia também, sabe, o quão especial ele era, né? Uma pessoa muito sensível, preocupada com os amigos. E tinha um lado humano muito grande, né? Então, com certeza, vai fazer muita falta da comunidade acadêmica, né? Por suas contribuições, tanto no sentido de agregar, manter as pessoas sempre por perto, né? Quanto fora dela, né? A gente perde uma pessoa realmente muito especial.
Olá pessoal, tudo bem? Meu nome é Gilberto.
Meu nome é Stephanie.
Somos alunos de doutorado aqui da Unicamp, éramos orientandos do professor Fernando. Queria dizer que é uma grande honra estar participando dessa homenagem ao professor.
O professor Fernando era um nosso orientador, ele era uma boa pessoa, sempre estava ajudando seus alunos.
O Fernando sempre vai ser um exemplo, tanto na nossa vida profissional, quanto na nossa vida pessoal. Como todo mundo já sabe, ele era um grande pesquisador, um grande professor e também um grande amigo nosso.
A notícia do falecimento do Fernando nos pegou de surpresa, mas sempre vamos nos lembrar dele como uma pessoa íntegra, um bom professor que sempre estava solícito em ajudar todos os seus alunos.
Meu nome é Mariana, eu sou atualmente pós-doutorando no IMEC. Até então, sob a supervisão do professor Fernando. Acho que todo mundo com quem a gente convive deixa na gente uma marca. E uma das coisas que foram bastante relevantes para mim foi a simplicidade dessa pessoa, né? Uma frase que é bastante característica dele e que representa bastante isso é uma que ele vivia me dizendo, né? Por favor, senhor, não. Meu nome é Fernando. E apesar de eu nunca ter conseguido chamá-lo, né, sem colocar um senhor ou um professor antes, isso me dá uma descrição, né, apesar de breve, de quem era essa pessoa.
Thank you, Carol. If there's anyone in the audience that would like to speak some words also in honor of Fernando before we finish today's session. So Fernando was my colleague here at IMEC, at the University of Campinas, and he was probably the kindest of all professors here in Campinas, and he was very well known for it to be always in a good mood, and we miss him terribly. So I'd like to, not sure if anyone would like to say something before we finish. So I thank everyone for attending today's edition of the Brazilian Algebraic Geometry Seminar in honor of Fernando Torres. All this material will be available, the talks and the video and the audio will be made available in the seminar's webpage later this week. So thank you very much, everyone, and stay safe. Stay at home and stay safe.